Hi Bernal, I got your email concerning your test. So I have here on the screen the first problem that you missed. This was number 4 on your test. The approximate z-score that corresponds to a right tail area of 0.37. Here on my paper I drew the normal curve, and you can see over here I have 0.37 in the right tail. And we know when we're looking for a z-score, as I showed you on the videos on Vimeo, that's always an inverse normal problem. But on inverse norm, your calculator always understands left tail areas. So if the right tail area is 0.37, then the left tail area is 1 minus 0.37. And that's what you needed to take the inverse normal of. That'll give you 0.33. I think you just took the inverse normal of 0.37. Is why you missed that one. The next problem that you missed is number 5. Find the z-scores that separate the middle 12% of the distribution from the area in the tails. Okay, so again I have that picture here. If I put 12% in the middle, then that means the area in the tails, which is sometimes referred to as alpha, is 1 minus 0.12 or 0.88. Now that's the area in both tails. So the area in one tail would be that divided by 2. 0.88 divided by 2 is 0.44. So in other words, you had 0.44 over here in the left tail and 0.44 over here in the right tail. And we want the z-scores that again correspond to those. So again, if you're looking for a z-score, that's an inverse normal problem. So here with the left tail of 0.44, if you inverse normal 0.44, that gives you negative 0.15. So that makes this z-score negative 0.15, and then since the curve is symmetric, then the z-score over here would be positive 0.15. Okay, number 6, you're supposed to find z sub alpha with alpha being 0.33. So in other words, you're looking for this. Now remember, by definition, a z sub number insinuates right tail. So that means find the z-score that insinuates a right tail area of 0.33, which makes this another inverse norm problem because we're looking for a z-score. But again, on this problem I have to take 1 minus 0.33 because your calculator only understands left tail areas. And so the answer was 0.44. I think, once again, you inverse normal 0.33, which gave you negative 0.44. Okay, the next problem that we had was number 9, where we were given this set of data, and we were asking, does this come from a normal distribution, basically. And so to do that, we had to do a normal probability plot. Okay, normal probability plots were explained in Chapter 7, Section 3. So what you wanted to do was enter this data into your list. I did that earlier. Here's that set of data that was just on the screen. Okay, and then it's second stat plot, and make sure plot 1 is on. The normal probability plot is this last icon, the one that's blinking all the way to the right, and then to get it we hit zoom and then 9, as is again explained on the video. So we get a normal probability plot that looks like this. Now remember, that means your population is normal if this plot is linear, and it's not normal if it's not. And you can see that this one doesn't look linear. We got the points going almost vertical here, and then so we have a big curve here, and then we curve again up here. So it kind of varies from your linear pattern that we'd have something like this if it was linear. So therefore, this data does not come from a population that is normal. So that was letter B. No, since the relationship between the expected z-scores and the observed values is not linear. Excuse me. And then of course, the last one that you missed was number 12. where you were given this set of data and you were asked to construct a confidence interval about the population standard deviation. Okay, so to do that, that's the one confidence interval that your calculator would not do. So we needed these two formulas. The one on the left is for the lower bound, the one on the right is for the upper bound. Obviously n is 12. There were 12 data values, so n minus 1 is going to be 11. Let's talk about the chi-squared values. So first I found alpha. At 95% confidence, so alpha would be 1 minus 0.95 or 0.05. Alpha over 2 would be half of that, would be 0.025. And over here I need 1 minus alpha over 2, and if you take 1 minus 0.025 you get 0.975. So if you go to your chart in your text then, in your chi-squared distribution, we would need 11 degrees of freedom because our sample size was 12. If you look up 0.025 with 11 degrees of freedom, you're going to find 21.920. And if you look under the 0.975 column with 11 degrees of freedom, you're going to find 3.816. And so those are the values that go here and here. And with everything substituted in, those two formulas would look like this. Now to get the S, the 10.721, I took the data and I entered it on my calculator. I did that over here in list 3. This is the set of data they gave us. And then I did variable stats. So I went stat, calc, variable stats is number 1. And then I have to tell the calculator where that's at. And since mine's in list 3, I have to tell it list 3. And again, this is something we did back in chapter 3. And there's your S, 10.721 basically. So that's where these numbers are coming from in the formula. If you put those numbers in, you get these two numbers. Now, these two numbers represent the confidence interval about the population variance. So to get the confidence interval about the population standard deviation, we have to square root those numbers. And if you square root those two numbers, you get these two numbers, which were correct. So hopefully that helps. Let me know if you have any other questions.